Hi, this info session will show you how Copernicus data can be used for coastal zone management and in particular for deriving spatial statistics useful for supporting the European Union's directives. The European Union issued various directives that impact the coastal zone directly or indirectly. For example, there is the Water Framework Directive, which requires member states to reach a good status for all the European waters, including coastal waters up to 2 nautical miles offshore by 2015 and to maintain and improve it up to the 2027. Another relevant one is the Marine Strategy Framework Directive, which concerns all the sea waters and requires to reach a good environmental status by 2020. The Water Framework Directive requires the measurement of a set of environmental indicators for evaluating the ecological status of a water basin. Coastal areas are included up to 2 nautical miles from the shoreline. The Marine Strategy Framework Directive defined 11 status descriptors to evaluate the good environmental status of all national sea areas. The Marine Strategy Framework Directive has been implemented by the Member States through a set of actions that usually includes the appointing of a national referent, which has the role of reporting to the European Union and which is responsible for the definition of the national monitoring strategy. This has to be done in harmony with what is done by bordering countries. The required monitoring usually consists of at-sea measurement and sampling campaigns, is assigned to national and local environmental agencies. For example, in Italy, the Environment Ministry is the national referent and coordinator for both water and marine strategy framework directives. The National Institute for Environmental Protection and Research, ISPRA, has the duty of preparing the reporting, providing scientific guidance, and defining practices and parameters to be measured. Finally, the monitoring is mainly delegated to regional authorities, which form a network with the mentioned institute. Currently, remote sensing of water quality parameters from satellite is a practice which has been done for more than 20 years. It can provide reliable results with the large area coverage and high temporal frequency. Gaps still exist in making them fully integrated with the current monitoring practices, but they are increasingly being considered a valid means to overcome the limits in spatial and temporal coverage of in situ surveys with respect to the requirements, e.g. for the mentioned European directives. Some of the parameters regularly obtained from Earth observation are chlorophyll A, water transparency, and sea surface temperature, which, for example, can be useful for evaluating the eutrophication status of a sea area. In 2016, the implementation of monitoring programs defined at national level was foreseen in order to complete the first cycle of QGIS assessment by 2018. Such programs are mostly based on traditional in situ measurements, which are not enough for the requirement assessment. The use of Earth observation can support the process by exploiting the existing long time series and the most recent sensors, like the ones on board the Sentinel-3 satellites. The in situ and the Earth observation measurements should then be used to perform statistical analysis to define and characterize representative areas in sea for each of the 11 descriptors. Technical roundtables involving member states bordering the same sea areas are being held in order to define the statistical figures to be proposed, and, more important, the definition of homogeneous areas for each descriptor of which to calculate such statistics. Such definition should be not affected by national borders. Long-time series of water quality measurements obtained from Earth observation can support the identification of homogeneous areas, for example, to identify areas with similar trophic characteristics. After the definition of such areas, the continuous monitoring by satellite can provide enough and consistent information to obtain the statistics for each area, to be used for the reporting for the directive. This picture shows a possible division of the Adriatic Sea in seed zones which showed a similar eutrophic behavior in the years 2007 to 2013. Such zoning was calculated with the Carlson Trophic State Index by combining chlorophyll maps from the Copernicus Marine Environment Monitoring Service and water transparency maps from the GMS, the precursor of Copernicus, MARCOST projects. In the following demonstration, a set of products from the Copernicus Marine Environment Monitoring Service and from GMS MARCOST will be used to calculate a set of statistics over the obtained seed zones. The maps considered will be monthly means of chlorophyll and water transparency over 1 year, from November 2013 to October 2014. This temporal aggregation is the same required for the Marine Strategy Framework Directive reporting. The software used are the Sentinel application platform, in short SNAP, which is a free tool provided by the European Space Agency, ESA, for processing the Sentinels and other remote sensing data, and QGIS, a cross-platform free and open-source desktop geographic information system application. After launching SNAP, we open one of the products obtained from CMEMS, containing the monthly mean chlorophyll from MODIS for the month of November 2013. The dataset has 3 bands. We display the CHL1 by double-clicking on it. The content of the CHL band is displayed as a grayscale image. We then activate the color manipulation panel. In the color manipulation panel, we can select various color ramps. We choose the simple 7 color. We then set the display minimum and maximum to suitable values. This is the resulting color-coded map. With the pixel info panel, we can read the chlorophyll values for each single pixel. The values of the chlorophyll map are expressed in milligrams per cubic meters. Now we open one of the water transparency map. We choose again the one for November 2013. The product contains only 1 band, corresponding to water transparency. We double-click on the band to display it. The content of the band is displayed as a grayscale image. We then activate again the color manipulation panel. In the color manipulation panel, we can select the various color ramp. We choose the gradient blue one. We then set the display minimum and maximum to suitable values. And this is the resulting color-coded map. With the pixel info panel, we can read the water transparency value for each single pixel. The values of the water transparency map are expressed in meters. Now we set the 2 windows view to show together the 2 maps. We can zoom and pan in any of the 2 windows, which are now linked. We can also use the navigation panel. We can, for example, zoom to the extent of the water transparency map. This is the result. Now we would like to visualize our zones. Selecting the CHL band, we can use the menu File, Import Vector Data, and select the shapefile format. Then we select the file and download it as separate polygons. The zones are displayed with different colors on the chlorophyll maps. Now, for convenience, we close the water transparency view. If we unfold the vector data folder of the chlorophyll product, we can see all the zones imported. Now, we would like to calculate some statistics for each zone. Such statistics be needed for analysis and reporting, as initially discussed. We collapse the vector data folder and we open the statistics tool from the analysis menu. This is the statistics tool. On the right, we can decide to calculate the statistics in different zones, named ROI. For example, we select the first 3 zones, and we launch the statistic calculation. This is the result. On the left panels, we can read various statistics, including the 90 percentile. Now we can take note of such values, for example copying them to clipboard and move to the next 3 zones, but it is not the best way to accomplish the objective, especially when we have a large number of zones. We can make use then of the graphic processing tool, which allows batch processing. This is an example of simple scripting. On the right, there is a GPT configuration file in XML format, and on the left, a parameterized executable file, which launches the tool separately for the 2 series of products, chlorophyll and water transparency. After we execute the batch file, we will have 2 shape files, as shown on the left, and 2 text files, which explains the names of the fields contained into the shape files. For example, for the chlorophyll statistic shapefile, the field P90THRS0 contains the desired 90 percentile, while for water transparency we are going to use the VRGBND1, which is the mean of the water transparency. To display the shapefile, we use a QGIS. We first open the zones shapefile. This is the zones shapefile which divides the Adriatic Sea in zone homogeneous with respect to the trophic behavior. We then open the 2 statistics shapefile. The other 2 shapefiles are loaded. Now we would like to display them in a meaningful way. We deactivate the last 2 and work on the chlorophyll one. By right-clicking on the CHL stats shapefile, we open its properties. In the Style tab, we set a transparent fill. Then we move to the Labels tab. We then select Show Labels for this layer, and we select the field whose value to display, that is the one containing the 90 percentile statistics. Then we set the style as bold, the size as 12, and the color as brown. Finally, we need to set the formatting of the numbers displayed. We choose to have formatted numbers with the 3 digital places. We then select OK. And this is the resulting layout. Now we would like also to apply a color scale to the 90 percentile for each zone. We return to the Style panel. We select the style Graduated and configure the panel as displayed. And this is the result. Now we set a similar style for the water transparency. Again, we set graduated style with a different color ramp and selecting the average band. The labeling is set as before. This is the resulting map. Now we can use the 2 map for visual analysis of the behavior of the Adriatic Sea area in the different zones. This, for example, is for the North Adriatic Sea, and this is for the South Adriatic zones, which are clearly oligotrophic areas with the clearer waters. In a GIS environment, it is easy for an analyst to extract the results, evaluate them, and combine with other layers, producing graphics and so on. Thank you for your attention.